All right, today before jumping into our lesson, we're going to do a little bit of a warm-up so we can do these together here. So it says convert 70 inches into yards. So we're going to start with our 70 inches. And I don't know personally how many inches are in a yard, but I do know how many inches are in a foot, excuse me. So I know there's 1 foot to 12 inches. And I put the 12 inches on the bottom because when I multiply, the units, the inches on top and the inches on the bottom, are going to cancel. This is referred to as dimensional analysis. We're going to use this quite a bit throughout this unit. I hope that you might have seen some of this in chemistry already. So now the inches will cancel and I will be in feet. But I don't want to be in feet, I want to be in yards. So I need to multiply by something else the number of feet in a yard. And there are 3 feet in 1 yard. So I'm going to put the feet on the bottom so they cancel. And I'm going to put the yard on top, so that's the unit I'm left with. Again, the feet on the top and the feet on the bottom are going to cancel. So what I have to do here is 70 times 1 divided by 12 and 3. So I'm going to take my calculator, 70, I don't need to multiply by 1, it stays the same. I'm going to divide it by 12, and then I'm going to divide it by 3. And I see here that I wind up with 1.94 yards. Again, I could keep more decimal places than that, but we're just really focusing on changing the units. For number 2, it says convert 40 hours into seconds. Again, I don't know how many hours are in a second, but what I do know is that there are 60 minutes in 1 hour. And because the hour is on top and I want it to cancel, I'm going to put 1 hour on the bottom, and then I'm going to put my 60 minutes on top. So when I do that, I see that my hour will cancel and I'm in minutes. But I don't want to be in minutes, I want to be in seconds. So I'm going to put, well, I know that I'm in minutes and I want to go to seconds. Well, I know that there are 60 seconds in 1 minute. So since minutes on top, I'm going to put 1 minute on the bottom. So again, they'll cancel. And I know that in 1 minute, there are 60 seconds. So now, when I multiply, my minutes cancel and I'll be left in seconds. So I'm going to have 40 times 60 times 60, all divided by 1, which I don't really have to divide. So 40 times 60 times 60, which gives me a very large number here. So I have 144,000 seconds. 144,000 seconds. Again, 1 and 2 are what's called dimensional analysis. We're just focusing on changing our units. And again, that's something we're going to be using in this section. For number 3, it says, if Gabe can run 8 miles per hour for 1.5 hours, or 1.5 hours, how far did Gabe run in miles? What about in feet? So we're saying she ran 8.5 miles. Well, I'm not sure if you know this formula or not, but distance equals rate times time. This is something we're going to come back to. Distance equals rate times time. So how fast did you go and how long did you go? So if we want to know how far Gabe ran, all we have to do is say the distance is going to equal the rate of 8, and that means miles per hour. So that's miles per hour times she ran for 1.5 hours. And if you notice here, just like we talked about before, the miles per hour, the hour's on the bottom, the 1.5 hours is on the top, the hours cancel, and you'll be left with your units of miles. So we can take our calculator, 8 times 1.5. You will need a scientific calculator for this lesson, by the way. So if you haven't already gotten one, make sure you grab one. All right, so she ran 12 miles, which answers part of the question. But the other part of the question says, how far did she run in feet? So just like before we were converting, we're going to start with our 12 miles. And now we want to go to feet. Well, I know I'm going to need miles on the bottom because I have miles on the top and I need them to cancel. And then does anybody know how many feet are in a mile? If you don't, you're going to want to write this down. There are 5,280 feet in 1 mile. And you'll see that the miles are going to cancel. And I take my 12 and I multiply by 5,280. So my answer here, I wind up with 63,000 360 feet. Always put your units, always put your units, always put your units there. So 63,360 feet. Quite a lot. She ran quite a long way. So number 4 says, if James is driving 60 miles per hour, how long in hours will it take him to travel 250 miles in minutes? All right, so first, how long did it ask, or how long will it take him, and then in minutes. So remember, our formula is distance equals rate times time. So here, it gives me the rate of 60 miles per hour, and it tells me that he wants to travel 250 miles. So what they've given me here is they've told me the distance, 250 miles, and they've told me how fast he's going to go. So that's my miles per hour. And what I don't know is the time. What I don't know is the time. So what happens here is I'm going to divide both sides by 60. Divide both sides by 60. And when I do that, my units are also going to be divided. So miles per hour. And when you divide by a fraction, you flip and multiply. So here, just looking at the units right now, I'm going to have miles over 1, that's the numerator, times, flip and multiply, hours per mile. You'll notice the miles cancel and I'll be left with hours. That's why this formula works, because if I'm solving for t, t is time. I need to have hours left. So I can take 250 and divide by 60, and that gives me, well, it gives me a non-exact number there. So I might want to use my simplified fraction because I'm going to be converting in a minute, but up to you. You can leave it as 4.17 hours if you like. For more specific purposes, we can leave it as 25/6 hours. Really up to you there. It's fine if you want to use the decimal version. I personally always prefer fractions. They're much more precise, but that's up to you. So the second part of the question asks for it in minutes. Well, I have hours, so again, I can go to minutes. And I'm going to use the fraction because I always like it to be exact. So I know hours has to be on the bottom because I have hours on the top and I need them to cancel. And how many minutes are in an hour? That's right, 60 minutes. So I'm going to put 60 minutes on top here. The hours cancel, and I grab my calculator and I multiply by 60. Sorry about that. Okay, all right, so I have 25/6 times 60. All right, which means I have 250 minutes. Again, these examples are just a warm-up, just kind of get you ready, remind you of some math that you might have done maybe in middle school or so with the distance equals rate times time. If you've taken physics, you've also seen this. Again, the dimensional analysis is part of chemistry. So now we're going to move on and talk about linear and angular speed. Again, you will need your scientific calculator, so if you haven't gotten it, you're going to want to do so. All right, linear speed. How fast a point moves around a circle and is symbolized by V. So we already know that speed equals distance divided by time, right? We just said distance equals rate times time. So the speed is the rate. How fast are you going? So if you divide by time, that means we have distance divided by time. And in this case, speed is referred to as velocity. The distance we're discussing is around a circle. We're talking about how far around the circle there, that arc length, and then time of... All right, sorry about that technical difficulty. I ran out of card space, but here we are. You can tell I made a wardrobe change. Regardless, going back to our linear speed, we're talking about how fast the point moves around a circle, and we're talking about point P. So we're saying this point is on the circle and it's going to go around the circle. How fast is that happening? And that's going to be linear speed. What we already talked about is that distance equals rate times time. So if we divide by time, that means the rate or the speed equals the distance divided by the time. Now, in math we tend to call speed velocity. And in this case, the distance, since we're going around a circle, is going to be the arc length, which we already talked about this unit. And then, of course, time stays the same. So we have velocity equals arc length divided by time. Putting these two ideas together, we can see that they are related to linear speed, or excuse me, angular speed. And angular speed is not about the point. but it is about the angle of the circle. And as the point goes around, how is the angle changing? That's what angular speed is about. So linear speed is about the point. Angular speed is about the angle because it's angular speed, so it's about the angle. Now, angular speed, it's important here, is symbolized by this fun little W. Don't worry too much about it, but it's a Greek W there. But we have W equals theta divided by time. Again, T is still time, but theta, it's important to recognize, is in radians. Theta is in radians. Theta is in radians. Theta is in radians. So here we have linear speed, and then we have angular speed. Linear speed is about how fast the point is going around the circle. Angular speed is how fast is that central angle changing. And we can relate the two of these together using some formulas you already know. So we said before, earlier in this unit, that S equals R theta. This is our arc length formula. S equals R theta. Again, theta was in radians. And we said just a minute ago that velocity equals arc length divided by time. So we have S equals R theta, so we can take that R theta, substitute it into the S. And when we do that, we wind up with V equals R theta, because the S becomes R theta, divided by T. Again, theta is in radians. But we can rewrite this as R times theta over T, because remember, it's like R over 1 times theta over T. It's the same thing, we just wrote it differently. The reason this is important to us is because theta divided by T, well, theta divided by T is our angular speed formula. So thus we come back to a very important formula you're going to want to memorize here. V equals RW. So linear speed equals the radius times the angular speed. So this formula, as well as the angular speed formula, are going to be the two that you really want to know. So V equals RW, and W equals theta divided by time. Those are our two main formulas, and the rest of our notes here today, we're going to talk about how to use those formulas. So, for example number 1, a ceiling fan with 16-inch blades rotates 45 RPMs. Now, RPMs, if you don't know, means rotations per minute. Rotations per minute. So, part A, find the angular speed of the fan in radians per minute. Alright, so for part A, it's asking me for angular speed. So a good place to start is always the formula. So W equals theta divided by time. So we have theta in radians divided by time. That's what we need to wind up with for our angular speed. But it looks like the only thing they really gave us to work with here is the 16 inches and the 45 RPMs. Well, 16 inches is neither theta nor time, so we're going to leave that on hold for now. Maybe we don't need that just yet. And let's work with this 45. So the 45 means that we have 45 rotations for every 1 minute. And that's close to what we need for angular speed, except for on top, we're supposed to have a theta, specifically in radians, and we don't have a theta. But on the bottom, we do have time. I see that there is a minute there, because it's per minute. So I need to change my rotations, and I need to change it into radians, because radian is what it asks for. Well, I'm going to use my conversion factors, just like I did in the warm-up there. Because rotation is on top, I know I'm going to need to have a rotation on the bottom. And if I'm thinking about a circle, how many degrees are in a circle? Very good. 360 degrees are in a circle. And if we think about it in radians, because theta has to be in radians, that means there's 2 pi radians in one rotation, because one rotation is a full circle. So one rotation is equal to 2 pi radians. This is an important one you're going to want to make note of if you didn't already know that one. Notice the rotations on the top, cancel with the rotations on the bottom, and now all I have to do is say 45 times 2 pi. Well, 45 times 2 is 90, so I have 90 pi, and that gives me radians per minute. 90 pi radians per minute. I answered in the units that they asked for, so I'm good to go. Again, this is the exact answer, my 90 pi. I could use a calculator, and I could come up with an estimated version of that 90 pi by multiplying through, and if I do that, 90 times pi it gives me 282.74. But the exact answer is always preferred. You want to leave your answer in terms of pi there, and you'll see why in just a minute. All right, so coming over here for part B, it says find the linear speed of the tips of the blade. Now linear speed, that's the V. That's V equals R W. Well, we already have W, and I'm pretty sure the problem gave us R. It did. It said the ceiling fan has blades of length 16 inches. So in order to do this, I'm going to say V equals 16 inches times, I have my 90 pi radians per minute. Now all I have to do is multiply. And again, I'm going to leave my answer exact. I'm going to leave it in terms of pi. So I'm just going to say 16 times 90. If you didn't already, by the way, make sure you grab that scientific calculator. You're going to need it. All right, so we have 1,440 pi, because we didn't multiply through by pi, so it's got to be in my answer. Now it looks like my units are going to be inches, radians per minute. But the thing that happens is when we multiply by another unit, the radians kind of just fade to the back there. We don't worry about the radians so much. When we don't have a unit, we assume it's radians, but when another unit comes in, we just kind of ignore the radians. So this becomes inches per minute. And I know it's a little confusing. We'll talk more about that further on in our notes here. So we have inches per minute, that's what it asked for, so I gave it inches per minute. And again, if you want to multiply through by pi, you could get your approximate answer of 4,523.89 inches per minute, which is very fast. There. All right, good on example number 1? Excellent. Let's try example number 2. The pedal sprocket of a bicycle has a radius of 4 inches. The wheels have a radius of 13 inches, and the wheel sprocket has a radius of 2 inches. The cyclist pedals 40 RPMs. All right, that problem already sounds a little scary. There's a lot of numbers in there. The most important ones, I'm going to go ahead and underline. So it gave us a radius of 4 inches, a radius of 13 inches, a radius of 2 inches, and then it gave us 40 RPMs. For part A, it says find the angular speed of the wheel sprocket in radians per minute. All right, well again, always start with your formula. W equals theta divided by time. And the only thing that they gave us in reference to time was 40 RPMs. So they gave me 40 rotations per minute. Remember, RPMs means rotations per minute. That's how many times it goes around in a minute. Again, this is very close to what we need for our angular speed, except I have rotations on top. Instead, what I need is theta. I need theta in terms of radians. So just like on the last problem, I'm going to need to convert. Because rotations is on top, I need to put rotations onto the bottom. And here's where I think about my conversion factor. I say, okay, how many radians are in one rotation? Well, one rotation is equal to 2 pi radians. So again, you'll see that the rotations on the top and the bottom cancel. And all I have to do is multiply here. So I wind up with 40 times 2 pi. 40 times 2 pi is 80 pi. And there I have radians per minute. It asked me for radians per minute, which means there's my answer. For part B, find the speed of the bike in inches per minute. Assume the wheels turn at the same rate as the wheel sprocket. Well, I'm looking for the speed, so that means I'm talking about linear velocity. So V equals RW. Good news, I already have W. So now all I have to do is figure out my R. I'm talking about the speed of the bike, and that has to do with the wheels, how fast the wheels are turning, how large the wheels are. So despite the fact that they give me 3 different radii, or radiuses, which isn't really a word, that's why we say radii, I'm going to use the one that has to do with the wheels, because I'm talking about the speed of the bike, and that relates to the wheels. So I'm going to say V equals 13 inches times my 80 pi radians per minute. Now I grab my calculator. Again, we're going to leave it in an exact term there. So I have 13 times 80. 13 times 80 gives me 1,040. Again, don't forget I had a pi in my answer, or I had a pi in my work that didn't cancel. So I've got to have a pi in my answer. Again, the radians are here, and the radians aren't canceling. But when I multiply by another unit, we just don't write the radians because we have another unit there. So I'm going to write inches per minute. The question asked me in inches per minute. I responded in inches per minute. So again, I'm done. I'm just using the formula. I know the problem sounds scary. I know the formulas look a little funny. We're talking about units, dimensional analysis. It gets a little confusing. But just start with the formula and fill in what you know. All right, example number 3. A cylinder with a 2.5 foot radius is rotating 120 RPMs. Again, first things first, it's always a great idea to start with the formula. So for part A, it says find the angular speed in radians per second. So for part A, angular speed, that's W. W equals theta divided by time. The only information they gave me that has anything to do with time is 120 RPM. So that must be what I'm going to start with. So I have 120. Remember, RPMs means rotations per minute. I already have the minutes on the bottom. That's great. But on top, I'm supposed to have theta. I'm supposed to have something in radians. I don't. I have rotations. I've got to change it. I have got to use my conversion factor. Because rotations is on top, I need rotations on the bottom. So I know I'm going to put my rotations down here so the units can cancel. And I know that one rotation, remember, one full go around a circle is equal to 2 pi radians. All right, so again, my rotations cancel. All I have to do is multiply. So I wind up with 240 pi, because I didn't multiply it, radians per minute. Oop, there's my A. Radians per minute. So for part A, it asked me, wait, is that the answer for part A? I circled it like it was the answer, but is that the answer? No, that is not the answer. And I know that's not the answer because I read the question. And that's really something that you're going to have to get used to doing in this section. Because here it doesn't ask for radians per minute. What does it ask for? Yeah, it asks for radians per second. So I can't leave that as my answer because although it is correct, there's nothing wrong with it. The problem didn't ask for radians per minute. It asked for radians per second. Okay, so on the next line, I'm going to start with my 240. Ooh, it would help if I wrote the number right. There we go. All right, so 240 pi radians per minute. Now, this is the angular speed. There's nothing wrong with it. I don't have to reuse the formula. Instead, I've got to do a conversion because it asked me in radians per second. So the radians are fine. I just need to change the minutes into seconds. Since minutes was on the bottom and I needed to cancel, I need to put minutes on top. And I need to turn it in to seconds. Well, I know that for every 1 minute, there are 60 seconds. That's my conversion factor. The minutes on the top and the bottom cancel. And then all I have to do here is divide. 240 divided by 60. So I can grab my calculator if you need to. If you just like typing it for fun, hopefully you can do that one in your head. If not, it's okay, no big deal. We wind up with 4 pi radians per second. And now I have my answer because now I have answered in the way that the question asked. The question specifically asked for radians per second, so I must give radians per second. All right, part B. Well, part B, I don't need another formula because part B says find the angular speed in degrees per second. Well, I already have the angular speed, so all they're asking me to do is change the units. Okay, well, that's fine. I can change the units. All right, so I already have W equals 4 pi radians per second. We just did that in part A. And the directions for part B say degrees per second. So I don't have to change the seconds because I already have them. What I now need to change is the radians. So since radians is on top, I need to put radians on the bottom so that they will cancel. Because on the top and the bottom, they're going to cancel there. So I need to know how many radians are equivalent to how many degrees. Well, we just talked about this when we converted at the beginning of the unit between radians and degrees. And I know that there are 180 degrees in every pi radians because pi equals 180 degrees there. So 180 degrees is the same thing as pi in radians. I can see that my radians cancel. Furthermore, I have a pi on the top and a pi on the bottom. They're going to cancel. That's why I don't bother dividing or multiplying through by pi because a lot of times they're going to cancel in your work. So now all I have to do is say 4 times 180. So I can grab my calculator if I need it, but I know that 2 times 180 is 360, and 360 plus 360 is 720. So that gives me 720 degrees, don't forget your degree sign, and that is per second. So 720 degrees per second. All part B was asking me to do is take what I already found and then convert it. Take what I already found and convert it. All right, part C here, because one part isn't enough. Part C, find the linear speed of a point on its rim in miles per hour. Okay, so find the linear speed. So I've got a formula for that. All right, I know that linear speed is talking about my V here. So for C, I have V equals RW. Good news, I already have W. And as a matter of fact, I think I have R too if we look at the problem. That's right, R equals 2.5 foot. So I know that V equals 2.5 foot times, now I have W. And the great thing about this is I have two options for W right now. Because in part A and in part B, both of those, I had W. I was working with different versions. Now you can use either one you want. One will require more calculation than the other. Personally, I always go for the smaller number, and I like to stay with radians because I have to do less work in the conversion there. You can use 720 if you want, but I'm going to go with 4 pi because it's a nice, easy number there. So I'm going to go ahead and put in and say 4 pi, and I was in radians per second. So I grab my calculator, and I can say 2.5 times 4. Oh, yep, there's 10. So I get 10 pi. Remember, the radians kind of fade to the back when I have another unit there that overtakes them. So I have feet per second. And this answer is linear speed, and there's nothing wrong with it except, did the question ask for feet per second? No, the question did not ask for feet per second. The question asked for miles per hour. So I need to respond in miles per hour. So I'm going to come down here. And now I need to do some unit conversion. So I have 10 pi feet per second. I'm going to go ahead and change the seconds first because I got to get seconds to hours. Again, I don't try to go directly to hours. Instead, I see seconds on the bottom. So I got to put seconds on top. And I know that there are 60 seconds for every 1 minute. And that's great for me because I can see here that the seconds are going to cancel and then I'll be left with per minute. But per minute isn't what I want. I need per hour. So again, I've got to do a conversion factor. And because minutes are on the bottom, I'm going to put minutes on the top so they'll cancel. And I know that there are 60 minutes for every 1 hour. Now, the minutes will cancel and I'll be left with per hour. So right now, if I multiply through, I have feet per hour. But again, I don't want feet per hour. I want miles per hour. So I've got to change my feet now. So coming over here, feet were on top, so I know I need feet on the bottom. And I'm going to miles, so I know that there's 1 mile for every 5,280 feet. Again, I told you that number would be important. The feet on the top and the feet on the bottom cancel, and now all I have to do is multiply through, and I will be left with miles per hour. So I grab my calculator, because these numbers are going to get kind of large. So you get 10 times 60 times 60, because if it's on top, we multiply by it. On the bottom here, I'm going to be dividing by, well, I don't really have to divide by the ones, I just have to divide by 5,280, which gives me, all right, I have 6.82 pi, don't forget your pi, don't forget your pi, don't forget your pi, pi miles per hour. And if you're curious about what that actually equals, about how fast it's actually going, of course we could multiply through by pi and get the rounded answer of 21.42 miles per hour. So this is the approximate answer. Again, I always prefer the exact answer, personal preference. I like to leave it in terms of pi, but that's up to you. If you don't want to leave it in terms of pi, I understand. If you need a brain break, go ahead and pause the video for a couple of minutes, do what you need to do there. Be open-minded. We're not doing anything hard, but I know that it is a lot, and I know it's tedious, and a lot of people, especially if you haven't had chemistry, you might have some trouble with our changing of our units here. So if you need a break, go ahead and take a break. All right, coming on back, example number 4 here. It says a tire with a radius of 9 inches is rotating 30 miles per hour. All right, it says A, find the angular speed of a point on its rim in radians per hour. Now, usually when we're finding angular speed, we're using W equals theta divided by time. Well, this time, they didn't give me rotations per minute, which is usually what I have. They did give me per hour, so I do have time on the bottom, but on top, I have nothing to do with theta. That's miles, and miles are a linear measurement, which tells me 30 miles per hour is not my W. 30 miles per hour is not my W, because miles is a linear measurement, which tells me I need to use my formula V equals RW, because W also shows up in this formula. W also shows up in this formula. So, okay, instead of them just giving me the information, the rotations per minute, and me making some alterations there, they've given me the linear speed, so they've given me V. Well, they also gave me R. So if I have R and I have V, I can just divide and find W. Hopefully it'll be that straightforward. I hope that it is. All right, so here we have 30 miles per hour. That's my V. Equals my R of 9 inches. And instead of writing MPH, that might be a little confusing. We'll go ahead and write miles per hour there. So I'm going to say 30 miles per hour. And then I have equals 9 inches times W. And the whole goal is to solve for the angular speed. That means solving for W. So now all I have to do is divide. However, I cannot divide miles by inches. That doesn't make sense. The units aren't the same. I can't say 9 inches goes into 30 miles this many times. They have to be the same units. I need them to be the same. All right, so I guess I've got to do some conversions here. So I have 9 inches. All right, so I've got to get inches into miles, or I can get miles into inches. It's really up to you how you want to do it there. I always prefer to go to miles, but it is up to you. If you want to change this one to inches, you can absolutely do that. So down here, I'm going to just do it on the next line. I have 30 miles per hour equals, I'm going to go ahead and move the W out front to get it out of the way so I can do my conversion. So I have W times 9 inches. And the problem is my inches. I've got to change my inches into miles. Well, again, I don't know about how many inches are in a mile, but what I do know is that there are 12 inches. Notice I put inches on the bottom so it can cancel with the inches on the top. There are 12 inches in every 1 foot. And here the inches will cancel, so now I'm in feet. Then I know that there are 1 mile for every 5,280 feet. Again, the feet on the top, the feet on the bottom cancel, and you'll see that I'll be left with miles here. So, as opposed to actually multiplying through all of this and making a really small decimal, I don't actually multiply it out, but I do simplify it here. So I'm going to write this as 30 miles per hour equals W times 9 times 1 times 1. That gives me a 9 on top with my miles. And on the bottom, I have 12 times 5,280. So I have 12 times 5,280. And on the bottom, I have 63360. You can divide this if you want, but make sure you're using the exact answer because this is going to be a really small decimal and you don't want to make any careless mistakes. So now here I have 30 miles per hour equals W times my fraction. So I'm going to divide both sides by 9 over 63360, and again we're in miles. Dividing both sides here, so 9,63360 miles. Keeping in mind the miles and my fraction would cancel, I'll be left with W on that side. When I divide by a fraction, what happens when I divide by a fraction? That's right, you've got to flip and multiply, and that actually goes for the units as well. So you'll see here that I have 30 miles per hour times flip and multiply. The 9 was on top, so the 9 goes to the bottom. Miles was on top, so miles goes to the bottom. On top now I have 63360. Notice the miles cancel. The miles cancel. So I have 30 times 63360, huge number, divided by 9. And here I have for my W equals 211200. Now, of course, it wouldn't be complete without units, and right now it just seems like it says per hours. But remember, when we don't have a unit, what do we assume that it is? That's right, it's radians. So here we have radians per hour. Radians per hour. And I know that was a lot. I really want you to understand. I just threw my pen down. Really want you to understand how that canceled out here. So if you have questions, go ahead and pause it and re-listen to that section. This is really important for you here. Now let me verify that we actually answered the question, because I was hate to have done all that work and not answer. It did say radians per hour. Okay, great. Did I answer in radians per hour? I did. Excellent. So this is my answer. All right. Of course, we're not done yet. We're never done. The problem just goes on and on. For part B, again, we're talking about angular speed. So that's nice. We're not using a different formula. But this time, it wants revolutions per minute. So it doesn't want you to find anything new. All it wants you to do is convert the answer that you already have. So right now, I have 211,200 radians per hour. And according to my problem, it wants me to give revolutions per minute. So let's start with the hour, because the hours should be a pretty straightforward one. If hour's on the bottom, that means I put hour on top, and for every 1 hour, there are 60 minutes. The hours were canceled, so now I have radians per minute. But they didn't want radians per minute. They wanted revolutions per minute. So I'm already in minutes. Now I need to get to revolutions or rotations. Either way, it kind of means the same thing there. All right, so I know my radians are on top, so I need to put radians on the bottom. And I need to have revolutions or rotations on top, totally up to you how you want to say it. The radians will cancel, but I need to know how many radians are in one revolution. That's right, a revolution is a full turn around the circle, so that means it is 2 pi. So 2 pi radians for every 1 revolution. Now I grab my calculator with that really large number, multiplying by 1 so it stays the same, then I divide by 60, and I divide by 2, which means I wind up with 1,760 revolutions per minute, or we can just write RPMs, means the same thing, rotations, revolutions per minute. However, this is not my answer. You have to look out. I had a pi on the bottom. So if I don't actually divide through by pi, then that pi needs to be in my answer. And again, this is an exact answer. I personally prefer this much more than dividing through, but if you're curious and you want to divide through and you want to get that estimation there, that is 560.22 revolutions per minute. And RPM, not M. Okay, all right. RPM, sorry about that. Get crazy with my units. RPM. Excellent. All right, so again, if you need to think back through that, part B had nothing to do with our new formulas. It had everything to do with changing our units. And we have a little pulley with a radius of 8 centimeters, and there's a belt that's going around them. There's a belt that's going around the two of them. And it's asking me for the angular speed of each pulley. Remember, angular speed is theta divided by t. Well, for their larger one, they gave me some good information here. So for the larger one, I know that it rotates 25 times in 36 seconds. So that means I have 25 rotations or revolutions. If you prefer, we can use revolutions. It's the same idea. Revolutions for every 36 seconds. All right, so we can divide that. And then we have to think to ourselves, is that what they're asking for? Is that how we leave? Our angular speed? And in this particular problem, they didn't tell us what our units are. They didn't tell us what we had to go to. So revolutions are not great. We want to at least go to radians, but after that, we don't have to go too much further than that because it didn't say to go further than that. It didn't tell us which units to leave it in, so we don't have to worry about it. So here I have revolutions per second. Of course, I want to at least get to radians because my theta is supposed to be in radians. So I put 1 revolution on the bottom because the revolutions are going to cancel. And then to 1 revolution, I have 2 pi radians. So here I can just multiply across or simplify my fraction. It's up to you. So 25 times 2 divided by 18. And when you do that, it gives you a crazy decimal. And I honestly really don't love that decimal. So what I would have done, instead of using my calculator, is I'm going to say, okay, I have a 2 and a 36. 2 on top, 36 on the bottom. Well, I know that 2 divided by 2 is 1, and 36 divided by 2 is 18. So now I can simplify this as a fraction and leave it as 25 pi divided by 18. Revolutions cancel, so we're left with radians per second. You could also write this, you could also have divided through and just said 25 divided by 18 times your pi, etc., and wound up with your answer. But up to you how you want to do that there. Up to you how you want to do that. All right, so we got the larger one, but the smaller one, it didn't really tell us anything. So let's pause right there, and I want you to pause the video, and I want you to see if you can't think about what information we might use. All right, so in this problem, what we know is that the radius of this one is 15, the big one's 15, the little one's 8, and they have a belt that goes around them. And while I know that the large one turns at this speed, that's how fast it's turning there, I don't know how fast the belt is moving. And how fast the belt is moving is not going to change from pulley to pulley. Even though the bigger pulley is going to turn more slowly than the smaller pulley because it doesn't have to turn as quickly, the belt has to go at the same speed. It's not like this part of the belt can go super fast and this part goes slow. The belt has to go at the same speed. But the belt is not affected by angular speed. The belt is traveling at a linear speed. So even though the question didn't ask me for linear speed, it is going to be beneficial to us to find the linear speed. I'm going to get rid of this because I didn't actually write the other one there. So this is the first part of my answer. This is for the larger one. This is the angular speed. But to find the angular speed of the small one, we need to use the linear speed of the belt because that's the only relationship I have to my 8 centimeter pulley there. So I'm going to go ahead and I'm going to find the linear speed because the linear speed is going to be the same for the big pulley and the small pulley because it has to be. The belt is traveling at the same speed. One part of the belt is not moving faster than the other part of the belt. They're moving at the same. So for my linear speed, I have V equals R times W. Well, I know the radius of the large circle here, of the large one, and I know its angular speed. So I'm just going to say 15 centimeters times 25 pi over 18 equals, oh, I forgot my units. Always, 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 always write your units. You want to always make sure you've got those there. Radians per second. All right, so when I multiply through, again, I could use my calculator and do 25 divided by 18 times 15, but it's going to give me a heinous fraction, and I don't want, or not a heinous fraction, excuse me, a weird decimal, and I need it to be exact because I need my answer to be exact for the other part. So instead, I'm going to say, okay, 15 and 18 have 5 in common, so that gives me a 3, so that gives me a 6, so 3 times 25 gives me 75 pi. Again, the radians kind of go away, and we take centimeters on top, divided by 6 seconds. However, I think I can further do that because 3 and 6, I guess they had more in common there. Oh, I made a mistake. That's why. Because if we're dividing by 3, this is 5. Look out for those careless mistakes. Everybody makes them. Look out, look out, look out. So I don't have 75 up here. Instead, what I really have, what I really have there is 125 pi centimeters over 125 pi over 6 centimeters per second. So this is my linear speed of the belt. This is my linear speed of the belt. Now this was not what the problem asked. What the problem asked is to find the angular speed of the big one and the little one. Well, we found the big one easily because they gave me information. To get the small one, however, I had to find the linear speed because the linear speed of the belt is going to be the same for both. So now that I know that the linear speed of the belt is the same for both of them, this linear speed is the linear speed for the big one and the little one. So I can use that idea to solve for the radius of the small one. So for the small pulley, we have the same linear speed. The linear speed is still 125 pi over 6 centimeters per second. I don't know the rate. Oh wait, I do know the radius. What was the radius? That's right, 8 centimeters. But what I don't know is the W. So here I have the linear speed equals 8 centimeters times W, and this time we have centimeters on both sides. So all I have to do is divide by my 8 centimeters. All I have to do is divide by my 8 centimeters. And when I do that, my centimeters will cancel, all right, and I wind up with, all right, if I simplify my fraction here, I wind up with W equals 125, still got the pi, over 48. The centimeters are gone, and now it just says per second. But we know that when the units go away, what are we really left with on top? Very good, we're left in radians. Again, the problem did not ask me specifically what units to put my W in, my angular speed, so I'm perfectly fine to leave it in radians per second. It did not ask me to leave it in an exact form. Now, I could just as easily have written the decimal equivalent. And if you're really like, oh my gosh, why did you write all these fractions up here? We can, of course, just actually divide it. And I could wind up with 2.60 pi radians per second. So again, that's up to you. If you want to use the non-exact answer, that's okay. Just look out for rounding mistakes, totally fine. All right, so, well, I guess this is the exact answer, sorry about that. So it's less exact. If you can leave it as a fraction, it's preferred, but it does still have a pi, so it's kind of exact. It's an approximate exact. All right, so one last example. If you're feeling good about this, go ahead and pause the video, see if you can't get started number 8 on your own. If you're like, oh my gosh, I'm totally lost, that's okay. We'll do it together. All right, number 8. A thread is being pulled off a spool at a rate of 69.4 centimeters per second. Find the radius if the spool if it makes 152 revolutions per minute. All right, so here, this one's a little bit different. For this one, they gave you a linear speed, and I know it's linear because centimeters are a linear measurement there. So this is my linear speed. Then they gave me revolutions per minute. So this is like on the way to getting my W. It's not W, but it's almost W, and it's asking me for my radius. That means my formula is going to be V equals R times W. So now all I have to do is plug into my formula. But before I can, this isn't really W here. I need to do a little bit more work to get to W. So I'm going to come over here on the side, and I'm going to find W. And for W, I have 152 revolutions per minute. The per minute is fine, I have no issues there, except up here it's in seconds, so maybe we need to change that. Most important thing is that we change the revolutions. So if I have a revolution on top, I have a revolution on the bottom, I want to go to radians. So for every 1 revolution, I have 2 pi radians. So here, revolutions cancel, and I'm left with, grab my calculator, 152 times 2, that gives me 304 pi radians per minute. However, we just said this is maybe not what we want to use because here it has seconds. So it's your choice. You can either take this one to seconds or this one to minutes. While we're here and we're already working with the W, I'm going to go ahead and change it into seconds. That way it just saves me some time later. So minutes are on the bottom. That means minutes are on top. I'm going to seconds, so 1 minute is to 60 seconds. Minutes cancel, so I have 304 divided by 60, which doesn't give me a super cute, it doesn't simplify easily, it doesn't divide evenly, so I'm just going to leave it as a simplified fraction, which means that W equals 76 pi over 15, and that would be radians per second. And again, you can start by dividing by 2 if you like there, no big deal. All right, so here I have, get rid of my email. All right, here I have my W. And since I have V and I have W, I can go ahead and just plug right in and get R. So V is 69.4 centimeters per second. R is what we're solving for. And I'm multiplying by that. And again, if you don't like that, we can just use the decimal version of our answer. It's totally up to you. Just make sure you're using the whole decimal. Don't have any rounding error there. So I'm going to have 76 pi over 15, and I have radians per second. All right, so when I do this, remember, I'm going to divide, and when I divide by a fraction, I flip and multiply. So this becomes 69.4 centimeters per second times, flip and multiply, 15 over 76 pi. And again, the units flip also, so the seconds are on top, radians are on the bottom. Centimeters on the top and bottom cancel. Remember, when we get another unit, radians kind of just fade to the back there. So now all I have to do is multiply through. So 69.4 times 15 divided by 76. So I wind up with 13 point. The 7 rounds the 9 up, so I'm going to go with 70 divided by pi, and that would be centimeters. This is how I like to leave my answer, but if you'd like to go ahead through and divide by pi, no big deal. So R equals 4.36. And again, units are important. Make sure you've got those centimeters there. So I took my W and I plugged it into my formula. Then all I had to do was divide. Don't be overwhelmed. I know there's a lot. There are two main formulas. W equals theta divided by T, and V equals RW. If you know those two formulas, you can do it. Try your best. There's a lot of unit changes. That's okay. We're going to practice them a lot, okay? Watch the video again if you need to. Good luck. All right, so example number 5, we have a cylinder with a 2-foot radius is spinning 450 RPMs. Remember RPMs, rotations per minute or revolutions per minute there. Find its angular velocity in degrees per second. So angular velocity, I know I've got a formula for that. So I go straight to W equals theta divided by T. Remember, theta is in radians and T is our time. So the only information they give me is a radius, which I don't need yet, and 450 RPM. So I'm going to go ahead and write my 450. And again, that's rotations per minute or revolutions per minute. Doesn't really matter, again, which way you call it. Actually, let's use revolutions. I like that one a little bit better here. So we're going to use revolutions per minute. And now I need to get a theta in there. As we've talked about before, this is the point where we're going to use our conversion because we need to convert from revolutions into radians. So since revolutions are on top, I'm going to put revolutions on the bottom. And I know for every 1 revolution, there's 2 pi radians because 1 revolution around a circle is 2 pi radians there. The revolutions cancel and I multiply across, so I get an angular speed of 900 pi radians per minute. Now 900 pi radians per minute is perfectly fine. However, it is not my answer to this question. I know it's not the answer to the question because it asked me for degrees per second. So again, I've got to do some rewriting here. So I have 900 pi radians per minute, and I need to change it into degrees per second. Well, let's go ahead and change the minutes first. I see that my minutes are on the bottom, so I need to put minutes on top. And I know there's 1 minute for every 60 seconds. And since the minutes are on the top and the bottom, they cancel, they cross out. So now I'm into seconds. Now I need to get to degrees. I need to get from radians to degrees. Since radians is on top, I need to put radians onto the bottom so they will cancel. And I need a relationship between radians and degrees. Thankfully, I know how to convert between radians and degrees, and I know for every 100 degrees, there are pi radians. Again, the radians will cancel, and I'll be left in degrees. So now I take my calculator, and I'm going to say 900, oh, remember, pi on top, pi on the bottom. Those also cancel. Look out for those pi's. So 900 times 180 divided by, on the bottom I have a 60. So I wind up with 2,700 degrees, that's how I mark it with my degree sign, per second. So there is my answer. Not that 900 pi radians per minute was a problem, that's still angular velocity, but it wanted it in degrees per second. So I need to make sure I answer the question how it was asked. For part B, it asks to find the linear speed of the rim in miles per hour. So for part B, I know I'm talking about linear speed, so V equals R, W. And all I have to do is multiply my R times my W. I see that my radius is 2 foot, so I can go ahead and put 2 foot in there. So I have V equals 2 foot times, now I've got a choice. I could use the radians per minute, or I could use the degrees per second. Again, I like this one a little bit better, my radians per minute. Since I'm going to miles per hour anyway, it's going to require less changing of my units. So I'm going to default back to my 900 pi radians per minute. And when I multiply those together, 2 times 900, that gives me 1800 pi. And again, the radians, when I get another unit, we kind of default to that other unit there. So that's going to be foot per minute. And again, there's no issue with this answer. This is a linear speed. However, the problem didn't ask me in feet per minute. The problem asked me for miles per hour. So I have 800 pi feet per minute. I'm just rewriting it over here so we have some more room to work. And I need to get this into miles per hour. And in order to do that, I need to change my feet and I need to change my minute. Let's go ahead and start with the feet here. So the feet are on top, so I need feet on the bottom so they will cancel, and I'm going to miles. And I know for every 1 mile, there are 280 feet. Again, the feet will cancel. Now I'm in miles per minute. I don't want miles per minute, I want miles per hour, so I need to go from minutes to hours here. So on top, I have minutes on the bottom, so I need minutes on the top. And I know that there are 60 minutes for every 1 hour. Again, notice the units cancel. When they're on the top and the bottom, they cancel. So I'm going to say 1800 times 1, which I don't really need to do, times 60. Then I'm dividing by 5,280. So I wind up with an answer of 20.45. Don't forget your pi, don't forget your pi, don't forget your pi. And there are my miles per hour because I had miles left on top and hours left on the bottom. So that is my miles per hour. So I have 20.45 pi. Again, make sure you answer in the units that the question asked. If you do not answer in what they asked, then it doesn't help you out. You're not going to get your right answer. Number 6. If a cylinder with a 6-inch radius is spinning 24 miles per hour, find the angular speed in RPMs of a point on its rim. Okay, so this one again, always look at the information they're giving you. For number 6, they gave us a radius, so that was nice. Then they gave us miles per hour. They didn't give us anything to do with revolutions or with radians. They gave us miles per hour. And because miles are a linear measurement, miles are something, on the ground, they're straight out. Miles, that is a linear measurement. So they gave me V and they gave me R. So instead of using W equals theta divided by T, I'm going to default to my linear speed formula because they gave me linear speed. So I'm going to use that. So I have V equals R times W. And in this case, we have here that V is 24, so I have 24 miles per hour. I know that R is 6 inches, and then I can very easily solve for W by just dividing. But oh no, just like the example we did earlier, I can't divide inches into miles. My units are different. I can't go dividing inches into miles. That wouldn't make sense at all. Instead, I have to change one. I can either change the inches or I can change the miles. And again, that's totally up to you. I usually prefer to change the inches. It's just out of habit. So I'm going to go ahead. Inches are on top. Again, the W is just kind of chilling out there. Don't worry about it too much. We'll deal with that in a minute. Inches are on top, so I need inches on the bottom. And I know that there are 12 inches for every 1 foot. So now my inches cancel and I'm in feet. And now I've got to go to miles. Feet are on top, so I put feet on the bottom. And there are 5,280 feet for every 1 mile. Again, the feet cancel. And now I'm in miles. So I can go ahead and say 24 miles per hour equals, I'm going to put the W first just to get out of the way. On top, I have 6 times 1 times 1. Okay, so 6 miles. And on the bottom, I have 12 times 5,280. So 12 times 5,280. That gives me 63360. Again, I'm not going to divide because it's going to make a terrible decimal, and I don't want to have to deal with that. Instead, I'm going to leave it right here as a fraction. And I know that I have to divide both sides by that fraction to get rid of it. And when I divide by a fraction, I flip and multiply, which means what I'm going to get here is I'm going to have 24 miles per hour times, because when you divide, you flip and multiply that fraction, flip and multiply, so I'm going to get 63360 divided by 6 miles. Notice the miles also went to the bottom, and the reason that happens is because the miles are going to cancel. They have to cancel. If they don't cancel, I'm doing something wrong. And this is going to be my W. And now all I have to do is multiply and divide here. So I have 24 times 633. Ooh, that's wrong. All right, yep. 63360 times 24. Sorry about that. Divide by 6. So I wind up with 253,440. Super large number, that's okay. Let's talk about the units. If we don't have units left on top, what do we assume they are? Good, we're in radians. And then on the bottom, we have hours left, so it's radians per hour. So here I have my radians per hour. But again, the important thing is to go back to the problem and find out if we answered the question appropriately. And sure enough, we didn't. Of course not. It doesn't want radians per hour. It wants revolutions per minute. It wants revolutions per minute. So we've already done the hard part. Now all we've got to do is change the units. So we have 253,440, and we have radians per hour. Now all I have to do is change it to revolutions per minute. Well, hours on the bottom, let's go ahead and change our hours. So that means I have 1 hour on top, and 1 hour is to 60 minutes. The hours on the top and bottom cancel, so I'll be left with minutes. Now I've got to change my radians into revolution. Radians are on top. That means I need radians on the bottom. That way that they cancel. One must be on top, one must be on the bottom. And I know for every 180 degrees, oh wait, I'm not going to degrees. That's not helping me. Instead, I'm going to revolutions. Going to revolutions. So for every 1 revolution or rotation, there are 2 pi radians. Always make sure you go into the right units. Don't just default into like, oh, I always love to go to degrees, go to degrees. Don't do that. Make sure you're reading and going to what they ask. So the radians on the top cancel with the radians on the bottom. And now I can divide through and get my answer here. 60 is on the bottom as well as my 2 and my pi. So I can go ahead and divide. So I'm going to divide by 60 and then divide by 2. So I wind up with 2,112. Look out, look out, look out. I still have a pi on the bottom, so I'm going to leave my pi in my answer. I want that exact answer there. So I have revolutions per minute or rotations per minute. This is my exact answer. If you prefer to divide through by pi and get the approximate answer, you can use 672.27 RPM. That would be the approximate answer, and that is okay too. Again, I prefer the exact answer, but up to you what you really want to do. All right, we're almost there. We've almost made it. Number 7. Okay, keep an open mind about this one. Keep an open mind. It sounds tricky, but I promise it's not that bad. 2 pulleys that are turning a belt have radii, that's the plural of radius, 15 centimeters and 8 centimeters, respectively. The larger pulley rotates 25 times in 36 seconds. Find the angular speed of each pulley in radians per second. All right, number 1 thing is always draw a picture if you can. So you got a big pulley with a radius of 15 centimeters.